Michaelis-Menten model can explain how substrate concentration could impact reaction velocity. First, we are going to plot the reaction velocity versus substrate concentration hyperbolic graph. From this graph, we could generally conclude that as the substrate concentration increases, the reaction velocity also increases from 0.1 to 0.2. We could see that the reaction velocity and the substrate concentration has a linear relationship. However, notice how beyond 0.2, line goes plateau. The point when the line starts to go plateau is the maximum velocity called the Vmax, which also means the maximum capacity of the enzyme. The line goes plateau due to the enzyme saturation. The enzyme is saturated when there is too much substrates for it to handle. At this point, no matter how much or less substrates are added, the enzyme simply could not react any faster. From the Michaelis-Menten model, people often interpret Km as Vmax over 2, but that is not entirely correct. Km is actually the substrate concentration at Vmax over 2.
So now I'd like to talk about a concept called the steady state assumption. An enzyme's catalysis could be divided into two steps. The first is the binding of enzymes to substrate, and the second is the formation of products. Both of these reactions have their own rate, and it is important to note that they are reversible. When the term steady state is used, we are implying that the concentration of enzyme-substrate complex, or ES, is constant. This means that the formation of ES is equal to the loss of ES. The forward reactions will be written as 1 and 2, while the reverse reactions will be written as -1 and -2. Since the reactions are thermodynamically stable, products do not go back to forming reactants. So we can assume that reaction -2 does not occur. So we can state that at steady state, the formation of ES would be reaction 1, and it is equal to the loss of ES, which are equations -1 and 2. Now we'll be moving on to the derivation of the Michaelis-Menten equation. As mentioned before, the steady state equation states that the rates forming ES is equal to the rates consuming ES. We can substitute the rate with the respective rate constants and reaction concentrations. As we know, the total enzyme available is equal to the concentration of the free enzymes added concentration of enzymes bound to the substrate. Using that information, we will substitute the value of free enzymes in rate 1 with the total E minus ES. Next, we can expand the equation and divide both sides by K1 to make sure that we end up with all the rate constants one side. We can express the combination of all the rate constants as a new term called Km, which I'll be explaining about later. Next, we will move all the terms containing ES on one side and factorize it out, and we will end up with equation 1. The speed of the whole process is the rate of formation of products, which is our rate 2, denoted by K2 times ES. So we will multiply both sides of equation 1 with K2, which gives us equation 2. When the speed of the process is at its highest, where VO is equal to Vmax, we can assume that all the enzymes present will be bound to substrates to form enzyme-substrate complex. So K2ET would be equal to Vmax. We can substitute this into equation 2 to come up with equation 3 called the Michaelis-Menten equation. Now let's talk about the term Km. If we assume that Km is equal to the substrate concentration and substitute that into our Michaelis-Menten equation, we will end up with Vmax over 2. So Km is defined as the concentration of the substrate when the reaction speed is at half of the Vmax. The catalytic efficiency is an enzyme's ability to catalyze reactions. Now a new term will be introduced called Kcat, which is equal to the maximum speed of a reaction divided by the total concentration of enzymes. This is called an enzyme's turnover number, which is the number of substrate an enzyme can turn into product in 1 second at its maximum speed. The unit for Kcat is second minus 1, or per second. We can define an enzyme's catalytic efficiency as Kcat over Km.